Given an integer array and a target, you may jump forward from index I to index j only when the value difference is within target. Return the maximum number of jumps needed to reach the last index, or -1 if it cannot be reached. From index 0 to 1, the value difference is 2, so this jump is allowed. From index 1 to 3, the value difference is 1, so this is another allowed jump. From index 3 to 5, the value difference is 2, so we reach the last index with 3 jumps. This path uses 3 jumps, and that is the maximum for this example. With target 0, a jump is only allowed between equal values. Index 0 can jump to index 4 because both values are 1, but from there the last value is 2, so the last index cannot be reached. Think of each index as a platform. A jump is allowed only when the value difference is within target. We are not looking for the shortest path, we want the most legal jumps that still finish at the last index. Let dp of I mean the best jump count needed to reach index I, start with dp of 0 equal to 0, and mark every other index as unreachable. To fill one destination j, look back at every earlier index I. If I is reachable and the jump from I to j is legal, then dp of I plus 1 is a candidate. A local rule like closest legal jump or farthest legal jump is not reliable, because that choice changes what future platforms can be reached. So the answer is not the biggest value anywhere in dp. It is specifically dp of the last index. If that entry is still -1, the destination cannot be reached. Initialize the dp array. dp of 0 is 0, because we start there with 0 jumps. Every other entry starts at -1, meaning unreachable. For each destination j, scan every earlier index I. If I is reachable and the value difference is within target, dp of I plus 1 can update dp of j. For j equals 1, index 0 can jump here, so dp1 becomes 1. For j equals 2, the reachable previous indices cannot legally jump here, so dp2 stays unreachable. For j equals 3, index 1 is reachable and the value difference is 1, so candidate 2 updates dp3. For j equals 4, the best reachable legal predecessor gives 2 jumps, so dp4 becomes 2. For the last index, several previous indices are legal. The best candidate comes from dp3 plus 1, so dp5 becomes 3. Return dp of the last index. We need the best jump count at the destination, not the biggest value anywhere else. Time is O of n squared because for each destination index, we may scan every previous index. Space is O of n for the dp array, one best jump count per index. Define the dynamic programming array, then for each destination j, scan earlier indices I. If I is reachable and the value rule allows the jump, update dp of j. At the end, return the last dp entry. Create the maximum jumps function with nums and target. Let n be the length of nums. Create dp filled with -1, meaning unreachable. Set dp of 0 to 0 because we start at index 0. Loop over every destination index j from 1 to n-1. For each destination, scan every earlier index I. Skip I if it has not been reached yet. Check whether the value difference from I to j is within target. If the jump is legal, update dp of j with dp of I plus 1. After all destinations are processed, return dp of the last index.